Hello everyone, this is my implementation of the SLAM algorithm on the RACECAR platform. So what is SLAM? SLAM stands for Simultaneous Localization and Mapping. It's a commonly used algorithm in robotics for navigation. SLAM allows the robot, as it moves through the world, to construct an understanding of its surroundings and then use this map that it's built to figure out where it is. This allows the robot to understand things in relation to the world instead of in relation to itself, and also take factors into account that are not immediately perceivable. Finally, this unified map gives the robot a convenient way to integrate all of its data that is coming from different sensors. So what sensors do we have to work with on the RACECAR platform? First of all, we have a color camera, which is just a standard camera. Then next we have a depth camera, which gives the distance from the robot of every pixel in the color camera. Then we have a LiDAR, which takes a 360-degree scan around the robot and gives the distance of each point. Finally, we have an IMU, which gives the orientation of our robot using pitch, yaw, and roll angles. Here are some of the challenges that we face while trying to implement SLAM on the RACECAR platform. First of all, we have a lot of noise and sensor readings. As you can see here, this is a LiDAR scan without noise, and this is one with noise. As you can see, it's a lot fuzzier and a lot harder to resolve fine detail. Next, we have a limited field of view and a low resolution, as well as a limited onboard processing power. However, the largest two issues that come from trying to implement SLAM on the RACECAR are spatial coherence and temporal coherence. Spatial coherence means that the SLAM map remains the same if we revisit the same point. As you can see here, this map is not spatially coherent because the robot made a complete loop, but as soon as it came back to a point that it had already seen, the map was completely rotated, which means it's useless for navigation. The next issue is temporal coherence, which means that the map needs to stay the same at different points in time. As you can see, it would be extremely problematic if we were trying to slalom between these cones and one of them suddenly switched to a red cone. This would completely alter our path planning algorithm. So our first step with implementing SLAM is to unify all of the different sensor data. We need all of the sensors on the LiDAR to represent their information using the same system. Then we can build an understanding of the environment that centers around the robot and thus extend it to the rest of the world. Currently, we're operating with 3 different coordinate spaces. The image space is the pixels arranged in an XY coordinate system from the image that is returned by the color camera and the depth camera, as you can see here. Next, we have polar space, which is built using which consists of radii and angles in a polar coordinate system that are updated as the LiDAR spins in a circle and measures the distance of every point. Finally, we have top-down space, which is our unified sensor system. It consists of Cartesian x and y coordinates and has the car centered at 0, 0. The good thing about this is that everything is in units of centimeters and it integrates all of our information into one top-down map. Here is the result of our top-down view algorithm. You can see as the robot drives around, we pick certain colors of interest from the color camera, we measure their distance of every pixel using the depth camera, and we place this on our top-down image, as well as our LiDAR data, which is converted from polar to Cartesian coordinate system. So now that we have our set of points for our local surroundings, we need to extend these into our world space. So this is done by sort of calculating the change in position and rotation between the points in the previous frame and the points in the next frame. This is done to stitch together each of the scans that we get every frame and figure out how to construct a map using them. The way we do this is using the ICP algorithm, which can calculate the exact rotation, position, and scale needed to match together 2 sets of points, as you can see here. So how does the ICP algorithm work? First, it takes every point in A and finds its closest neighbor in B. Then it calculates the transformation needed to move all of these points in A as close as possible to their partners in B. And it repeats this process until the average distance between every point in A and every point in B is within a certain threshold. It then returns an affine or homogeneous transformation matrix that defines exactly how A needs to be moved, rotated, and scaled in order to fit with B. So here's the results of our ICP implementation on the RACECAR. We're giving the ICP algorithm all of the LiDAR data as well as a random sampling of the rest of the top-down view. This includes our color and depth camera data. This makes our SLAM implementation more robust since we have more sensors feeding into the same algorithm, and it also means that our car can actually navigate using just the floor markings because we can take into account the color of certain objects and they don't necessarily need to be in 3D. The issue with this is that the ICP implementation is a little bit slow and it sometimes fails to converge. Every time there's a hitch over here, that's when the ICP algorithm cannot figure out how to match the previous set of points to the next set of points. And this causes issues in our implementation further down. So, once we have the transformation given by the ICP algorithm between the previous and current frame, we can integrate these changes over time to get the robot pose. The ICP algorithm gives us this transformation matrix, as you can see here. In order to get our robot position from this transformation matrix, we can start with our initial robot position at 0, 0, and then add to it the x and y components of our transformation matrix every frame, giving us a running total of our x and y coordinates of the robot in the world. Next, to fit our puzzle piece of a scan into the map, we also need to keep track of a running transformation, which tells us how to rotate and scale the points. This is done by starting with the identity matrix here, called K, and then every frame calculating K of n plus 1 based on the transformation that is given by the ICP algorithm between the frames. Then we can use K of n to transform all of our points on our local view and place them into our map. So here are the results of the localization algorithm. This is done with only the x and y coordinates as mentioned before. As you can see, the position of the robot is plotted as these yellow dots over here, and as it's navigating through the scene, you can see its path traced out on the SLAM algorithm's map that it's building up continuously. So, as a conclusion, this solution has the basic elements of SLAM. You can see here that as the robot navigates through the space, it is localizing itself with the surrounding objects, and it is trying to build up a map. Unfortunately, the limitations of the software and hardware platform make this a little bit impractical. First of all, the LiDAR and our other sensors have too much noise, as you can see by the fuzziness of the lines that are coming out over here. And the ICP implementation often fails to converge or simply takes too long. There are some improvements we can make, though, which I didn't have time to implement. First of all, we can reinforce the SLAM algorithm with techniques such as Monte Carlo localization or particle filter localization. This gives us a more reliable position estimate, and we can use that to reinforce the position estimate that was given by our ICP function. We can also use a probabilistic ICP algorithm, which has better convergence characteristics and also better noise rejection, which can help us with the issues with the data that I mentioned before. Finally, we can implement a loop closure or graph solving algorithm that can correct our data from previous scans based on new information. This helps a lot with spatial coherence. Finally, we can corroborate our top-down SLAM implementation, which uses primarily the LiDAR data, with an RGBD or depth camera SLAM implementation that relies solely on the color camera and the depth camera. By using these two sensors separately, we build a more robust end result, and this helps with spatial coherence. Thank you for watching.